In fact, whenever current changes in any part of a circuit, EMF will be generated to resist the change. And this is called self-induction, because self-induction means it's happening in the same circuit. So the inductance of a coil not only tells you how much magnetic flux it is creating, but it also tells you how much EMF is being generated, which opposes the change in the supply EMF. So, looking at the circuit on the right, if the current through a coil is increasing, that means EMF is increasing. The self-induced EMF is in the opposite direction to that supply EMF to reduce it. But if the current is decreasing, that means the supply EMF is decreasing and the self-induced EMF tries to make more, and so it is in the same direction as the supply EMF. So this is another case of Lenz's law. We can look at a circuit with a resistor and an inductor, remembering that the inductor only has a voltage across it when the current is changing. This equation for the voltage around the circuit shows that E, the supply EMF, must, by Kirchhoff's voltage law, equal the drop in potential across the resistor, which is IR, plus the change in potential being generated by the inductor, and that is L times di dt. So this is called a differential equation because one of the terms is the derivative of the current or the change of current with time. And the solution to this equation has an exponential form. So it looks like this. At the top right, we see that the current, if we assume that a switch in the circuit closes at t equals 0, then the current will start at 0 and it will rise not instantly, as we used to assume with resistors, but will rise over an interval of time to a final equilibrium value. You can see at the bottom right there the graph of the voltage across the resistor, which shows the same shape as the rise in the current. So the voltage across the resistor, which is 0 when there's no current, rises to its final value, which would be I times R. And since the potential difference across the inductor must equal the supply minus the potential difference across the resistor, we can see that as the potential across the resistor rises, the potential across the inductor drops to 0. So we can see from the equation I equals E supply EMF over R times 1 minus E to the minus RT over L. Now if T is 0, then E to the 0 equals 1, and that shows that our current is E over R times 1 minus 1, which is 0, which we know. When T becomes very, very big, E to the minus infinity, let's call it, becomes 0. So then our current just becomes I equals supply voltage over R, which means that the inductor now is just acting like any piece of wire because the current isn't changing. And so all the potential drop is across the resistor. Now, just as we had a time constant for a capacitor that was another element in a circuit whose behavior changed with time, we have a time constant for our inductor. And it's a similar thing. It represents the time for the current in the circuit to rise to about 63% of its final value. So if we have a circuit with an inductor, the battery needs to supply more energy than in the circuit if it just had the resistor and no inductor. Part of the energy delivered by the battery is used as the internal energy in the resistor. So if it was a globe, it'd light up. The remaining energy is stored in the magnetic field of the inductor. So if we look at the power in the circuit, going from our equation from the last slide for the potential differences around the circuit, remembering that power equals potential difference times I, we then have that EMF times I equals I squared R in the resistor plus I times L di dt. So epsilon times I is the rate at which energy is supplied from the battery. I squared R is the rate at which energy is being dissipated in the resistor. And that means that Li times di dt is the rate at which energy is being stored in the magnetic field. So if we let U stand for the energy stored in the inductor, it is equal to L times I times di dt. So to find the total energy, we integrate over the current as it rises from 0 to a final value of I, and then we simply get that energy U equals a half times L times I squared. And this is our expression for the energy stored in an inductor. Now, you might remember back to our working out the energy stored in a capacitor, which is a pretty similar form. There the energy was a half times Q squared, where Q is the charge, and then C is the capacitance.